So I put a track together and I did some examples on a track yesterday. And I know that that was pretty fast, and it was just as the bell was ringing, we were talking about the change in momentum during a collision, right? That match up with yesterday. So track and green car and yellow car. Now, when I set up a collision problem in my head, I do try to kind of stratify what the problem is about, but also I try to, I'd encourage you to do this, set it up in your head as a instantaneous before and instantaneous afterwards. So we talked about that yesterday. So in this example, let's assume the green car was moving and the yellow car was at rest. And the green car had a mass of, let's go with 500 grams. And let's say the yellow car, 250 grams. Let's say the green car is approaching at 2 meters per second. And after the collision, let's say the green car was going at 0.5 meters per second. I'd like to know how fast the yellow car was going. Just so you know, this is like a physics honors level question. All right, I don't mean that derogatory. I mean, this is very, very basic. It's to kind of give you a way to organize yourself. In a collision is the instantaneous moment before contact and the instantaneous moment after contact. And I know you're probably going to wonder why I'm saying that over and over again. It's because of what your homework is like. So I'm going to label this side before and this side after. The collision occurs in the middle here. Now, I'm not picturing the actual collision. I'm picturing the events before and after. But where the collision goes, I always like to place a reminder there to tell me to think about the fact that momentum is a vector quantity. Now, for the time being, we're going to be dealing with one-dimensional collisions. But this is perfectly applicable to multiple dimensions. So if you have a 2 or 3-dimensional collision, this all works the same way. But our math is only one-dimensional. So even if we had a 2-dimensional collision, we'd be breaking it up into 2 one-dimensional problems. You follow along? Because we've talked about stuff like that before. Now, what I said yesterday is that if you add up the momentum of all the objects before the collision, momentum of the green car plus the momentum of the yellow car, and if there are more cars, you could just add them all up. They would have to be equal to the momentum of the green car and the momentum of the yellow car and whatever else happens to be there. You see, the idea is, in any closed system, individual objects can be interacting in that system, but during an interaction, whatever amount of momentum is gained by one object, it'll have to be lost by another object, so that the momentum of the system stays the same. Now, yeah, we're only going to be usually talking about 2 objects interacting at a moment, not usually 3 or 4 at once. It's hard for 3 things to collide all at once, but it's not hard for 2 things to collide and immediately later have 2 other things collide. Either way, whatever number of items we're talking about, the momentum of the system stays the same if there's no external forces acting on the objects. Now, all that means for us is to take the mass of each object and multiply by the velocity before the collision. So the mass was 500 grams, that's 0.5 kilograms. And I don't know that you have to convert to kilograms for this. If you leave all of it grams, it'll probably be fine. I just am used to converting to kilograms. So I will, especially if they ask for things about energy and stuff. It's nice to already have it in terms of kilograms. I'll move on to the next object. That's a mass of 0.25 kilograms, but it was at rest before the collision, so its velocity is 0. Well, that has to equal the mass of the green car and its new velocity plus the mass of the yellow car and its new velocity. The first thing I need to kind of point out to you and be very explicit, a conservation of momentum problem generates a single relationship, a momentum relationship that equates the state of the problem before and the state of the problem after. And I know you're not writing this down, but you should. There can be only one unknown in such a relationship because there's only one relationship. This isn't like our prior problems where we generated a system of force equations, where we had lots of substitutions to do to get there. In these problems, it's going to come down to the fact that there is one momentum relationship, and it's before and it's after. There can be only one unknown. It might appear like there's other unknowns. They're just hidden in the problem somewhere. So they can ask about a mass, they can ask about a velocity, and that's about it. Now you guys see what you have to do here, right? And hopefully you've already begun the process of solving for the answer. And many of you probably already know how fast the yellow car is going. Is that true? So, Nika, how fast is the yellow car going? 3 meters per second. Wow. Seems like a lot, doesn't it? But when something big hits something small, sometimes something small is moving pretty fast afterwards. It's true. All right. Good so far? Is this relatively easy? There are 3 common types of collisions. You've just seen one of them. Let's talk about another one. A very common collision is one in which the objects stick together during the course of the collision. So in a laboratory setting, you put a piece of tape or Velcro between the 2 objects. And when you do that, they might be stuck together. It's also not uncommon for there to be like a train car problem where there's couplings between the train cars, and when one train car contacts the other, they now are coupled together. But in order to make this a truly new question, let's consider the before case a little bit. What if in the before case, the yellow car were also moving? I'm going to intentionally trick you. Don't be tricked. What if the before case, this is the situation, and the cars are going to stick together due to the collision? Is this a problem you can do, or do you see my trick? What's the trick? Yes, sir.
The green car wouldn't catch the yellow car.
That's right. The green car wouldn't catch the yellow car. There'd be no collision. Always look at the reality of your problem. Don't go in blind. They could easily make a situation in which there is no collision. So in a situation where there is no collision, be able to state there is no collision. So I don't really want to trick you. So let's, there you go. Now you have a true problem. Work it out. See what you can get. This one's on you to figure out. I will call on one of you in about 30 seconds. So when you worked it out, you found out that this was 1.5 meters per second. Both cars have the same velocity, but we call this a perfectly well, if I spell it right, that'd be better, perfectly inelastic collision. Now, a perfectly inelastic collision is a subset of inelastic collisions. Inelastic is any collision that has a loss of energy. Okay. All inelastic collisions, the energy after the collision is less than the energy before the collision. And we're generally talking about kinetic energy in this sense. So most collisions in nature are inelastic. A perfectly inelastic collision is one in which the two objects join together. Okay, they're stuck together. And in so doing, they tend to lose a lot of energy during that process. So the word perfectly here doesn't mean there's anything perfect about them. It's just that they have a lot of loss of energy, perhaps a maximum loss of energy in a perfectly inelastic collision. So they don't have to tell you the objects stick together. They can use the vocabulary word instead. And you're to note that because it says perfectly inelastic, the objects stuck together. Yeah?
Was there a name for the first one where they didn't?
It was just an inelastic collision in that there was nothing special about it. You had two objects that interacted, a certain amount of energy was lost. Now, as you can probably imagine, there is the possibility of a elastic collision, which is funny because we don't call them perfectly elastic, even though there's something somewhat perfect about them. What do you think is the result of an elastic collision? What do you think is special about it?
All the energy is transferred from one body to the other.
Not necessarily transferred from one body to the other, but there's no energy lost in the collision. So in an elastic collision, the energy stays the same. We don't usually ask questions about elastic collisions, and it's not because they're particularly hard, it's because they're mathematically tedious. You see, in a elastic collision, the kinetic energy of the cars is equal both before and after the collision. So in one of those collisions, as you can imagine, we have the cars before and the cars after. So we'd have an equation that equates the energy before and the energy after and the momentum before and the momentum after. So we can generate two relationships. Now, again, not particularly hard, but because you're generating two equations, you can have two unknowns. You follow what I'm saying? So in this one, we might not know either velocity for the cars after the collision, because in an elastic collision, I generate enough information by saying it's elastic to generate a way to figure out both velocities. And it's not particularly easy either. For example, I'm going to flesh this problem out so you can see what it looks like, okay? To flesh it out, I'm going to go ahead and put in what the momentum equation would look like before and after, and put in what the kinetic energy equation would look like before and after. So let's start with the momentum equation. The momentum before will be 0.5 times 2 plus 0.25 times 0.5. And that's got to equal 0.5 Vg plus 0.25 Vy. Not hard, but if all we had was momentum, we wouldn't be able to solve this, right? Because we have two unknowns. But then we can bring in kinetic energy. So the kinetic energy before the collision, 1/2 0.5 V squared plus 1/2 0.25 V squared. Oops, wrong velocity. And then after the collision, 1/2 times 0.5 times Vg squared plus 1/2 times 0.25 times Vy squared. Again, generates two equations and two unknowns. There are special situations where you can do an elastic collision. It doesn't take very long. A good example of that would be something like billiard balls. Again, not truly elastic, but can be treated close to elastic because they do have a very elastic collision. But when you're playing billiards, all the billiard balls are the same mass, right? Since they're all the same mass, all the masses cancel out, making these pretty straightforward to solve. Does that make sense? Now, I'm not gonna spend a lot of time with these. They don't happen very often on the exam, and as you can tell, they would be mathematically tedious to complete. And I don't wanna make this about some kind of tedious second semester Algebra 2 problem. That's what this is. You solve the top for one velocity, because it's the one that's not squared, and you plug it into the bottom, right? That's what you do. You will get two answers for the velocities. The only hint I will give you is that in these problems, when you solve for VG or solve for VY, there'll be two answers because it's a quadratic, right? One of the answers will be the initial velocity. So you'll know one of your answers because it has to be. There's only going to be two conditions that satisfy the problem, and the initial condition's one. So every one of these factors, because you know one of the factors already. You follow me? So you can do these, but they're tedious. And because they're so tedious, I generally don't ask very many questions about them. The block is pulled to the side and released, and it swings down to here, hitting this block, knocking that block off the table. But this block was not stopped during the collision, and it kept swinging until here, where it stopped there. Clearly, it must have slowed down due to the collision because it doesn't swing all the way back up. Does that make sense? There's lots happening in this question. Before I even read what the problem is, sometimes it's nice just to break the problem down into its parts. So I want to use this picture. I can draw the problem down into its parts. And I'm going to make the block that is pulled backwards, the green block. I know. And the block that is at the bottom, the yellow block. And I'm going to draw the green block here. And I can draw. I don't need to. I know how to draw-ish. Wow, you guys are so weird. Don't know what's wrong with you people. So I'm going to need to see this guy, three times? So let's see, I need him here, and I need him there, there, and there. So let's put him in all places. We're going to have him here. And then here. And then here. That look okay to you guys? That's what the green block does. Now you might not know why there's two in the middle. I'll explain. And let's talk about the yellow block. So the yellow block is here. And that okay? So I am segmenting the problem on purpose and drawing parts of the problem that weren't really there. All the way on the left is the initial state of the problem. This block is going to swing down and hit that block. That block should rest on the table. Now, in looking at this, going from here to here, I call this part one of the problem. And that's part one, just the block swinging downwards. Then the green block strikes the yellow block. That's, I think, part two of the problem. And then multiple things happen in part three of the problem. But from here to here, which I'll call part three, the green block swings upwards, but the yellow block is a projectile and hits the floor. So the yellow block, had some range along the floor, while the green block swung up to some angle. Good so far? Now, when I look at part one, I see a clear conservation of energy question. The green block changed its height. It started from rest and went from having gravitational potential energy here to having kinetic energy here. That's got to be a clear conservation of energy problem, because the green block, the only thing that happens is it swung downwards, converting its potential energy to kinetic energy. Now from part two, that's the instantaneous moment before it strikes the yellow block and the instantaneous moment after it strikes the yellow block. So just before it strikes the yellow block, I think it's the only one that has a velocity. After it strikes the yellow block, I think it's got a velocity and the yellow block has a velocity. There's evidence for why I think the green block has velocity. What's the evidence for why I think the green block has velocity? Still swung afterwards. That's right. In fact, I think there's another conservation of energy question that takes place in part three as the kinetic energy of the green block is converted back to gravitational potential energy as it comes to rest at some height. All look good? I've taken the problem and broken it up into its steps. So you see, there's a collision problem in this problem. And it's relatively small, and it's right here in the middle. But there's a lot of other problem here, too. Now, if you were writing a question, like you decided to write a question, you could tell me, how long the string is, because that's how high the block was drawn upwards. You could tell me where it hit the ground over here. That would tell me how fast the yellow block is going. Right? There's lots of things when it comes to problem solving that we can do as problem writers in this question, but ultimately we can put the problem together. Right? There's mgh for the green block has to equal 1/2 mvg squared for the green block, right? That has to happen. And then I see a collision where there's mvg for the green block has to equal mgvg for the green block after the collision plus myvy for the yellow block after the collision. Now the green block swings upwards some, so there's still going to be 1/2 mvg squared after the collision, and that's got to equal, well, I remember this, but maybe you don't, mgl times 1 minus cosine theta, because I remember things. I hope you remember things too, right? That if you want to figure out how high something is due to the angle it makes, then I can pull that right out of my my long-term storage because I committed it to memory. Did you commit it to memory? If not, I would commit that to memory because they give us the length of the string. I know I'm going to use the length of the string here for this height, but if I am asked about this angle or I am given that angle, I had better use that later. So what I've done here is I've traced a problem out for the green block. And yeah, there's also a problem here for the yellow block that probably is going to involve me going and looking at the vertical and horizontal stuff, saying that, y or delta y is going to be whatever the height of the table is, and vy naught is going to be 0, and the acceleration is going to be g, and I'm going to have to figure out how long it takes the block to reach the ground. And the range and vx is going to be equal to vy after the collision. And t, right? I'm tracing out a problem. I'm forming a strategy. I'm looking at the parts of the problem and breaking it up into its pieces. There's a collision here, but do you understand that the collision part is probably not particularly interesting here? Collision is just momentum before equals momentum after. I see no point in doing 20 of those in a row when it's just going to be momentum before, momentum after. The mistake you're going to make is forgetting to decide what direction is positive and have anything go the other direction and mistakenly put in that it's all positive velocities. That's the mistake you're going to make. Tomorrow we're going to do a little bit more on this, and I'm going to have a little bit more, some of the more complicated situations. But